Good afternoon, everybody. Thank you all for coming along, and I'm very happy to share a talk with you about part of my career that's been as acting as an expert. Of necessity, it's based around my experience in the UK and some projects outside the UK, so it might not necessarily apply, or some of the laws and rules may not apply to South Africa. So please do check if you find yourself doing these things. It's particularly nice because in 2014 I was president of IStructE, and one of our visits was to South Africa, which was one of the nicest moments. That I noticed that Tony Smith is on the talk, so very nice to see you again, Tony. 5 parts. The first bit is just a little bit tongue-in-cheek about how I became a civil structural engineer. A little bit about the company that I work with, which is Perega. We'll move on to a selection of cases that I've investigated over the years. The rules of being an expert, which, as I say, probably apply, but you just need to make sure that they really do apply to South Africa. And then a little bit about insurance and staying out of trouble, which is a nice place to be in the first place, I think. So, inspiration for me was my maternal grandfather. He was an aeronautical engineer in the Second World War, and he worked for a firm called Napier, and he made engines for some of the fighter planes. And I've still got some of the tools that he used to make these. And I just thought, sort of 10-year-old kid thinking, wow, that's something that I would like to do. So I started at school. I realised I needed A-levels, and then I realised I needed to go to university. And most of my school life was centred around sport. But before then, this is a picture of the front of one of the aircraft engines. 1940, no notion of a digital age, no computers. Everything was done by hand and feeler gauges. And when you look at that and think about the engineering, or this is mechanical or aeronautical engineering, we would find it quite hard to do that even now, so let alone then. So, one of the things we did at school, in the 4th year, we did metalwork and woodwork, which according to the school was engineering. And I invented a floating stool. And the idea of the floating stool was that this very arthritic lady could put her feet on the stool. It would then inflate to raise her legs to the horizontal. And then when the doorbell rang and she wanted to go and answer it, you pressed a button and the stool deflated. So I had my moment of fame. The press came along, took the photographs, off they went, and she said, right, how do I deflate this thing? Press the button, and it didn't work. So one thing, we did eventually we got the stool to work eventually, but one of the things, of course, about what civil and structural engineers do is that it really has to be right first time. There isn't any real room for failure. I went to Greenwich, University of Greenwich, and everything that I remember, I learned. The things that I was taught, I think if you're taught, it means that you're inspired, and if you're learning about things, you're inspired. So all the things that I remember at university are very much the practical things. This is my geotechnical model of a retaining wall in the final year. And my parents were very supportive. They said, look, we'll support you through university, but you've got to stop doing all that sport. You need to knuckle down and learn. So day one of university, I joined the sailing club, which has been my passion ever since. And for me, sport is really important. I do a lot of cycling, I do a lot of sailing, and that's a photograph of me having played the then world number 4 at squash. That's John White. So I say to the students when I lecture them, keep on top of your sport, and that will look after you. So very, very quickly about Perega. We were formed in 1947. 6 offices in the UK, 85 staff. So the pandemic saw us dip a little bit, and in this financial year we've taken on 15 really good engineers. We're active in various sectors: health, education, retail, but the only thing we really don't do is heavy civil engineering work. And in 2019, we became an employee-owned trust. So the company is now owned by a trust on behalf of for the benefit of the employees, which we really think is a very strong point. So, a few cases. I will say that most of the cases that I've looked at, and hence the ones we're going to look at today, are around foundation failure. And I found that civil engineers, structural engineers that come out of university and start to practice really don't know as much as they ought about soil mechanics. So this slide is very simple. It shows a foundation and it shows what happens when you get general shear failure. And we'll see some of those later. I put this one in because a couple of the cases are about the failure of fibrostone columns, where the horizontal resistance from the ground, the surrounding ground, was insufficient to allow the stone column to support the required weight. And pressures on the foundations, well, one of my first cases is all about this, where a pressure bowl is very much like what you see on the left-hand side. The 45-degree slope where pressure is supposed to dissipate is really a bit of a myth. And this whole question of the bulb of foundation pressure has caught a lot of people out. So, on to the first one. This is a basement in London, in Mayfair. Mayfair is one of the sort of posher parts of London, if I can put it like this. And this building that we're looking at, about 200 years old, and the client wanted a basement constructed under the whole of the footprint. So the building itself is a collection of load-bearing masonry, load-bearing brickwork construction, pieced together over the years, but in relatively good condition. Underneath the building is one of the old rivers of the River Thames. So a lot of the rivers have been culverted, covered in. Some of them run in tunnels, some of them just run through gravel, some of them just run through the ground. And one ran right underneath this building, called the River Tiber. So, the way in which the basement was constructed was that steel columns, on the left-hand side, steel columns were placed in slots cut underneath the foundations. So the bottom of the steel post rested on the ground, and it was jacked up against the underside of the foundation. So what happened was that the loading was transmitted from the foundation here, down through these columns, onto these base plates, and these jacks were there to transfer the load from the foundation down into these columns. And then the plan was to construct a piled raft underneath the building, between all of the steel columns, construct a reinforced concrete wall incorporating the steel posts. Now, unfortunately, very little site investigation was done. The client decided that would all be done once the contractor was appointed, because when contractors do site investigations, of course, they do them for free, but we all know that it's included in the cost. So what happened was that the load of this building was transmitted down here and into some of the soft alluvial materials that were formed by the old River Tiber. So not immediately, but gradually the building started to settle underneath its own weight. Here you can see some of the very congested area where the construction took place. These are the steel columns that were being put in. Some of them were simply bricked up underneath the foundations, whereas others under the main wall were jacked into place. There again, we can see some of the work that took place. It's fair to say not well supervised, and this is the photograph of the floor slab having been constructed. You can still see the steel columns in here. You can see the reinforcement that's been put in place for the concrete walls. And one morning, at the start of the day, the contractor noticed cracks forming in the superstructure. They started to monitor it. By about 10, 11 o'clock, the cracks had got even bigger. They called out the engineer. They then had to evacuate the whole of the building because the cracks were getting wider. Various types of profession in the building. And then by about 7 o'clock in the evening, part of the building had collapsed. And you can see very, very dramatic. Fortunately, all the people occupying the building had managed to get out. And there again, you can see the nature of the construction of the building. A lot of it was timber, load-bearing construction. So an example of how not to do underpinning, a lack of appreciation of how you transmit loadings from the underside of a foundation down to a lower level. The foundations, over 200 years, have compacted the soil beneath them, and the soil had become in equilibrium with the weight of the building. And by transferring that load further down into much softer material, caused the gradual settlement and the collapse of this part of the building. So, the sort of things that we take away from this, really do think about site investigations and make sure that your client understands the need for them at the beginning, not when the building's starting to be constructed. Think about investigating the building. Again, the client wouldn't pay for investigation until the contractor was on build. One of the two partners of the consultant working on the project was the director of the piling company that was employed to construct the foundations, and that person checked the piling calculations, which were later found to be in error. So there was a clear conflict of interest in there. The engineer did accept in hindsight that they should have been more thorough. They should have been far firmer with their client about investigating the building rather than let matters progress as they did. This one is a building in England, and I will just mention that all of these cases have been settled. They are of some age, so there's no commercial issues in me telling you about these things. And some of them I haven't left out. Naturally, I've left out some of the things which are confidential. So, steel frame building in England. The idea was that first floor level to the underside of third floor level was going to be a clear opening with seating around the outside. Part of the building was a library, part of it was an exhibition centre. So you can see the cross-section this way. And the important thing to note is that at this level here, fourth floor level, between fourth floor level and fifth floor level, is a truss. And the truss is suspending with these 3 hangers here, 4 hangers here, suspending this floor. And this section applied as you go through the building. So a very large atrium area through the building. You can see that there. So, as we would all analyse, you've got your truss, you've got the loadings from the hangers, and you can sketch fairly easily the direction of the forces. So, all fairly straightforward stuff. This one was put into a computer model a few years back now, so an early version of a computer model, and it was modelled like this. So all of the loads were applied to the top of the truss, no loadings on the bottom. So, as we all know how to design trusses, these loadings, according to the computer output, were 0. The connections, as we'll see in a minute, the connections to the at the end of the truss here were not very well made. And fortunately, the fabricator put minimum connections into each of these hangers. So there was something like 4 M20 bolts in as a minimum. So although the force in theory was 0, there was a certain amount of capacity in the truss. So this is the topping out ceremony. We got up to the top level, it's been concreted. We've all got our high-vis jackets, we've got our hard hats, and we're all safe and sound. 20 minutes later, just after the building had been vacated, that's what happened. So, one of the things you see from this is that it's not a particularly robust building. There's not many load paths, and here we can see one of the trusses lying across the, you know, all the other stuff. You can just about see the connection there. And the failure was partly the hangers, partly the building, the floors beneath failing, pulling the truss in, and some of the connections just failing. So we can see it there, we can see it there. This was a sketch that was done at the time, showing broadly what the connection looked like and where the inception of the failure took place. And that was a sketch that we produced simply to show the difference between a robust connection and one that isn't robust, so that all the forces are going back into the body of the truss rather than relying on very, very simple web plates to transmit that force. And I suppose the thing that you really learn from this one is that anybody can work out loadings. We can all do load takedowns, but you need a certain amount of experience, and I think to be, you know, an experienced engineer to know what to do with those loads. And had somebody really just taken a step back, not got carried away with the model, not simply tried to do all of the design within the model, I'm sure that that would have been spotted and this wouldn't have happened. So this one here is a gas pipeline. So, like South Africa, I think I showed this one to people when I came in 2014. But like South Africa, we used to manufacture a lot of our gas by burning coal and forming coal gas. What's happening now with natural gas or imported gas is that it's transmitted via 1.5 metre diameter pipelines at 150 bar of pressure. So if you take a 1.5 diameter pipe, its cross-sectional area is about 1 metre, give or take, and at 150 bar, you have 150 cubic metres of stored gas per metre length of pipe. So, just bear in mind this country lane and just bear in mind this footbridge here, because it's relevant in a minute. As time went on, the roads developed. This is the line of the gas pipe, goes underneath this busy dual carriageway. And this is a map taken from some of the old Ordnance Survey maps. This is the old country lane that went through here. This is the A road, which we'll talk about a little bit more in a minute. This is where the gas pipe went under. And then this road then became a dual carriageway. So a very, very busy, very important road that runs north to south in Kent. And this is a picture of the way in which the gas pipes are put together. So number of gas pipes, they're all welded together, they're ultrasonically tested, and the pipes are lowered into the ground. And as you would imagine, relatively little site investigation needs to be done. We're simply digging the trench, we're putting the pipes in, and we're covering them up. Just another picture here. This is what happens at the change. This is what happens at changes in level, and this is an enclosure here where they're doing some welding. When we get to a road or a canal, because this pipe's gone under a couple of canals already, you have an auger, and the auger is taking the material out of the front of the pipe that's being put into the ground, and you can see here that in soft ground, the pipe is jacked in, the auger is inside the pipe, augering away the material. In harder ground, the auger is advanced slightly outside the pipe and augers away the material, and then the pipe is jacked along its route. And you can just see it here. This is a pipe being jacked into underneath the road, and this is the motor and the jacking point here. Now, just look at this. This here is a previous attempt to go underneath the busy road, higher level, and you can also see it here, and it's been blanked off. So what happened is that this pipe was being jacked underneath the road. The road is just at the point there. So you can't see the material that's coming out of the face of the cutting until it comes out of the auger position. So what they said was that they were looking at a very firm clay. All of a sudden, it started to become slushy. They started to see fragments of brick, and they also found parts of an old signpost. You remember that signpost that we saw in the picture a few slides back? And what had happened is that the whole pipe jacking had come across the old bridge, the old route of the river, and caused a collapse in the highway. So this is a very, as I mentioned earlier, very important highway that runs north to south in Kent, and just completely undermined. And this is a void here, which was formed because you've got the old part of the footbridge, you've got the very, very loose alluvial material which was associated with the old stream bed. And there again, we can see another picture of the damage. And this is what happened. The county council became very concerned about the stability of the road. I think unnecessarily, in my view, but we ended up having to dig an extremely large hole to take out the remains of the bridge, take out the remains of the old river. And it wasn't really the fault of the client that was there. Here you can see positions of pressure grouting going into the ground. And all of this took about 6 months. And this building that you can see in the back here its trade relied on this road being open all the time. And over a period of 6 months, this business was nearly put into receivership. So, the lessons from this one. There were no site investigations of critical points. So you would think that each side of a crossing, a road crossing, a canal crossing, there would be some site investigation. There was no site research, so nobody looked at the historical maps, nobody looked at the types of things that might cause problems along the route of this pipe, and a mistake that really could quite easily have been avoided. And the issue seemed to be that there were so many, the pipeline was so long, and the budget was the budget. They just carried on and really didn't investigate too much. So sources of information, local records, place names. Sites will often reveal their past. So things like Foundry Road, Marsh Road, Cemetery Lane, and even asking the lady at the bus stop, which I've done on more than one occasion. If you're investigating a site, you can strike up a conversation with somebody, and it's surprising what they might tell you about the history of the site. This one is in eastern England, and this is another old gasworks. So again, all of the coal being burnt here, and the coal gas being put into these gas containers here. As time went on, the gasworks became redundant. These are the 3 gas holders again. And by this time, there's a spoil heap that's been constructed here by some works that are being carried out here. This is a completely separate from the gasworks site. It's not water; it's just colour blue for recognition. So this is an embankment. This is a sort of a plateau level. There it is in a bit more detail. So there's the circular gas holder. This is the plateau here, which has been built up over time. And don't ask me why, but the local housing developer got permission to build a housing estate on the top of it. Perhaps they thought that the views might be quite nice from the top of this mound. And there we can see it there. So this is the gas holder. This is the mound here. This is about 80 degrees. And I'll show you some plans in a minute. They're not very good quality, unfortunately, but this mound was increased in height. The face of the mound was stabilised using tensile reinforcement, so geotechnical material. And before that was done, the ground beneath this mound was improved by vibro stone columns. Again, not the best of site investigations, but the vibro stone columns were augured down, filled up with stone, and that was intended to support the additional weight of this embankment. So there again, we can see another picture of it. So you can appreciate the steepness of the embankment that's been formed here. Again, building works in progress. This is a cross section through the mound. If you can imagine, the gas holder is somewhere here. This is the original profile. It was vibro compacted. This is the line of the additional material. This is the side of the embankment. This is not a very good drawing, I'm afraid. This is really just showing the positions of some of the vibro compaction that was put in on the toe of the wall, where the bund was increased in height. And there we can just see some cross sections here showing some of the tensile reinforcement that was put in. This photograph here is after the embankment had failed. The loading that had been applied had caused a deep slip of the ground. These lorries here were all parked normally, side by side, on a hard standing. And what we can see here, and the sheer scale of it makes it difficult to appreciate, but all of this has mounded up. All of the lorries have been pushed upwards and sideways. This has moved downwards and caused a very, very large shear failure across a wide area of the ground. This is the gas holder. The gas holder was piled and held 250,000 cubic feet of gas, which is 7,500 cubic metres. And after this happened, there was emergency works to get the gas out as soon as possible. Again, difficult to appreciate the amount that the ground has risen, but you can see here, this is the gravel around the side of the gas holder. This has been moved up by about 2.5 metres. This pipe here is level, and this fence line used to be level with the pipe. So you can see how that fence line has been pushed up as a result of the failure of the ground. There again, we can see the effect of the, this is just a small part of it. These are the gas pipes that go into the gas holder. The gas holder was simply being used to store excess gas from the gas grid. That's just a shot at the side showing the failure of the A-frame supporting the gas pipes going into the gas holder. These are about 2 metres deep, these chambers. And again, you can see the amount of heave by the smaller crack at the bottom, the larger crack at the top. As I say, it's very, very difficult to appreciate the extent of the failure of the ground, because it's very, very difficult to photograph large areas of it. So a classic shear failure, but on a very, very considerable failure, a very, very considerable scale. Very little thought had gone into the strength of the materials below the bund, and I just think some sketches and a bit of thought would have informed the process. And what happened? This is the gas holder. This is effectively the bund, which had dropped downwards, and very, very large shear failure that had occurred. And when I talk to students about this, the analogy is very much like a triaxial test. You're putting load on the top, which is the additional weight of the bund, and you're applying different levels of lateral pressure. And there'll come a time where your clay specimen that you're testing in here will fail under shear. What happened in this case is that the ground on both sides of the stone column just wasn't strong enough to support the lateral forces that were there, and that's what caused the settlement. Very little that could be done to remediate the situation. What happened was that the side of the toe of the embankment, if you remember, it was about 80 degrees, was raked backwards. The housing plan was modified. So further back here was okay, but this whole area here was repiled, restabilised, and a lot of the weight that was associated with the front of that embankment was just taken away. So the lesson to take away was think about the additional loadings and think about risk. This one is in Norwich. So Norwich is a nice little city in Anglia, in the middle of sort of East England. A very, very simple task. So this is some old, very, very low-lying industrial buildings. A quite tall masonry wall running at the back, acting as a retaining wall. And at the bottom here, all of these huts here sit on a concrete oversight. And the plan was to take away the oversight and construct 2 or 3 detached houses. There's a house here, and the only access to this house is via a road that runs along the top of this wall and out into the highway. Just behind here, this is a line of houses along the main road, and the access to that house is just running behind here. They demolished the lightweight buildings, they took up the slab, and unsurprisingly, the toe of the wall simply went forward and collapsed. And with it, the whole access road that runs along the back of the wall here, just see the wall there. The road ran along the top there, and you can see the end of the road there. So as well as having to reconstruct that wall, the owners of the site had to compensate the owners of the house. Both of their cars were parked outside the house at the time, so the cars were stranded there for about 6 months. So there was the cost, not only the cost of this, there was the cost of providing the homeowners with a walkway just behind the trees and two cars to use whilst the whole thing was being repaired. So the amount of damages to the wall and the homeowners was almost the same as the cost of building the houses. Lessons to take away. Does the structure look proportionate, and what holds the wall up? And I'm sure there's a lot of you scratching your head saying, well, quite obvious, isn't it? You would dig some child pits, you would have a look at that wall. These large masonry walls are there with a very low factor of safety, but there's lots of people who wouldn't do that. This one is very serious. Somebody driving this crane survived, but life-changing injuries. Up in the north of England, so this is the failure of the base of a tower crane. And as the crane came down, it wrapped itself around an adjoining building. These pictures come from one of the newspapers. So again, you can see what happened here. So it's a luffing jib crane. So as just for context, that's the tower. This is the jib. So the jib can go anywhere from there around to the horizontal, and it's balanced by a counterweight at the back. So the counterweight is quite clearly counterbalancing the load there. When the jib is right up here, the overturning moment on the base of that crane is almost as high as the overturning moment there. In fact, this is the design condition with the jib right up. So first thing that went wrong was the analysis of the four pile cap. The people that designed it worked out the moments about this axis. They didn't work out the moment about this axis, because if you work out the moment about that axis, you've got one pile in tension, one pile in compression. If you do it about that axis, you've got two piles in compression, two in tension. So that was the first mistake that led to the under-design of the piles. To compound that, they also misread the crane loadings from the manufacturer. The third thing that happened was that this is the base of the crane. So you get these four lugs that are concreted into the top of the pile, crane pile cap, the pile cap, and it's all part of a framework. But unfortunately, the positions of the 4 feet of the crane coincided with the positions of the piles. So what did they do? The pile reinforcement was 20mm diameter bars, 6 of them arranged in a circle, and a 32mm high tensile Divideck bar, which is really just a very high tensile bar, that was supposed to be cast into the top of the pile, into the pile cap, bent over, and it was that bar alone that was designed to provide the tensile connection between the piles in the crane base and the crane base itself. So they cut that off. They drilled 6 20mm bars into the circumference of the pile. The bars should have been grouted in by 450mm, and they were not. The average depth of grout was about 150mm, and worse than that, if you look at a 20mm diameter bar, a deformed bar, its outside diameter was 22.5mm. So they drilled a 20mm hole, they somehow hammered the thing in. It didn't leave any room for the grout that should have gone in there. So not only were the bars too short, they were also very, very poorly grouted in. So an extremely poor connection. When it was investigated, it was found that some of the bars, these are the bars here with the red hats on them, were outside the circumference of the helical reinforcement. Some of them considerably so. So all sorts of things here just didn't go right, and it was poorly supervised, poorly constructed, and poorly designed. And really, basic statics would have told somebody that they had got the pile design wrong, the design for the pile, the crane pile cap. How things fit together. They really should have looked at the crane base and had a look at where the piles were going. And have a think about the critical things to inspect when you're doing this type of remedial work. Nobody was suggesting the remedial work was easy, but it really didn't. It was so important to get right that it really needed to be inspected. Cross-laminated timber, something that's becoming quite popular in the UK. This one's in East London. I'm not an architect, but the house doesn't do much for me. But on this side here is a retaining wall up to this level. just normal strip foundations, and then you construct the building with cross-laminated timber panels, and the rules are that you have to construct them on a plinth, which is 250 millimetres tall, really to keep the base of the panels out of any damp and any water that might escape from taps and things like that. What happened, again, there were a number of water leaks in the flats. This here is the retaining wall that we saw on the left-hand side of the building. The retaining wall leaked, started to affect the cross-laminated timber, and over a period of a couple of years, the bottom of the laminated timber started to rot away to the extent that it became structurally unstable, and the whole of it had to be supported by an internal system of maybe shores and maybe struts. You can see them all there. And the lesson to take away here is who is responsible for what. The cross-laminated timber supplier was responsible for the design. The consulting engineer was responsible for the ancillary design and the design of the foundations. It wasn't clear who was responsible for the waterproofing because it wasn't in the architect's or the structural engineer's appointment. So that was really what caused one of the problems. The consulting engineer also overstepped the mark and started to get involved in some of the design of the cross-laminated timber. So when it came to unpick all of this, nobody really knew what was happening. So the thing to remember is make sure that everything is covered in your brief, and make sure that things that are important that are not in your brief are put elsewhere. Just looking at this one very, very quickly. This is a system-built car park, and there were a number of these built around the UK about 10 years ago. Problems with the connections at the sides here causing the truss failure. Somebody did say to me, well, they're only Audi cars, it doesn't matter. But I just put this one in because if there are many of them, you just need to make sure that you have the right controls in place to make sure that there isn't a systemic design error that's going to replicate itself. And the last one is an oil terminal. This is in Bumpsfield, just to the north of London. And in 2003, there was a huge bang in the early hours of the morning. The terminal was one of the tanks of the terminal was being filled with oil. There was a leak, and over 250 square metres of the site was covered in fuel oil, which then ignited and caused a huge explosion. We live about 25 miles away on the opposite side of London, and we even felt the blast. And this is typical of the damage that was occurring to buildings. This isn't on the site at all. This is about half a mile away. And our client had a similar building that we had to help repair. And our client had a building which was a portal frame unit with a curved roof. And there's a number of, there was a suspended grid ceiling underneath, and there was a number of air-conditioned units that were built into the suspended ceiling. So what happened to our client's building was that the blast came across the top of the roof. The suction caused an upward movement of the roof. By the time the blast had gone past, the roof came back down again, but the very, very heavy weights, the inertia was still going upwards. And what happened was a number of the units unhooked themselves from the ceiling, and this is what happened. So this is inside the client's office building, and thank goodness it happened on a Sunday when there was nobody inside. So sometimes things are unforeseeable, just to bear that in mind. So I want, in the time that remains, I just want to talk very, very quickly about the rules about being an expert. They apply to the UK, so just please do check that they apply in South Africa as well. I think certainly the basics do. So, do you have a conflict of interest? That could be quite wide-ranging. Personal contacts, company contacts, client contacts. It might be that the person, your opposite number is a very, very good friend. So you need to think about that. It might be you have a very good professional relationship with somebody who's on the other side. So all of those things you need to think about so that you can not only take a balanced view, but be seen to take a balanced view. So will other people see your views as balanced? Are they your clients? Are they your contractor clients? I've had a number of occasions where I've had to turn down expert appointments because of the issue of conflict, and you just have to make sure that you get that absolutely right at the beginning. Remember, it's not your fault. So many people think when they're an expert, they are there to defend the other party's actions, and they start to take it personally. And you're not there to say what you would have done. You're not there to be an advocate if you're instructing solicitor's client. And your sole duty is to the court or other jurisdiction. So it might be a mediation, an adjudication, an arbitration, or just a straightforward court case. And hard as it might be, don't take it personally. It's not your fault. It's not your problem. You are there to provide objective evidence to allow the court to reach an appropriate decision. There's always shades of grey. Barristers, of course, operate in black and white, but we're engineers. We know that rarely will one side be completely right or completely wrong. What are your instruction solicitors' clients' strong points? That's good, but make sure you tell them about the weak points as well. Solicitors won't always be interested. They only want to see the good news, but believe me, barristers like to see the whole lot. And if you're a good expert, you'll test the presumptions on both sides and help your client see where his or her weak points are, because it's far better to do that now at the outset than it is in court. And the test is what a normally competent engineer experienced in the type of work being undertaken would have done. And what was that person asked to do? Did they do it? Not what you would have done. It's not about hindsight. And do bear in mind that you can't be an expert if you're also dealing in the remedial works, because if you're dealing in the remedial works, then to be an expert in describing that, you won't be seen as wholly objective. So just bear that in mind. It's nearly caught me out once. And your report. It's your report. It's nobody else's, and it will be you and nobody else that's asked to defend it if it goes to court. It will probably have things in there that your instructing solicitor doesn't want to hear. And one of the best accolades I got from a barrister is, well, Nick, you didn't tell me everything I wanted to hear, but at least I know where I stand and I know what you're going to say. So just bear those things in mind. It's you are as an experienced engineer as the solicitor and as the barrister. So you're there to give that evidence and not to be trodden on. And just a little word, sometimes people swap experts. Either the expert perhaps becomes ill, retires, perhaps the expert's expertise is outside, is beyond what they can really do. So if you're asked to replace somebody, make sure that you understand in writing that the other expert's appointment has been terminated. Courts don't really like replacement experts. Sometimes it happens. You just need to be absolutely clear why it's happening, why you're being involved, and that that you are the only expert acting in that particular field. Unless it's clear at the outset that other experts need to be involved. So last part of it, staying out of trouble. A little bit about insurance companies as well. And again, do check that the rules in South Africa are the same as they are here, but these are really guiding principles. So professional negligence insurance is about reducing the risk and transferring the risk, making sure that we take on the things that we are competent in and that we don't somehow get hooked up on things which are really nothing to do with us. So our insurance brokers, we use Griffiths and Armour in the UK. They operate elsewhere. And it is about teamwork and it's about long-term relationships. It's not necessarily about the cheapest policy. It's about the most robust policy that you can have, and it's about making sure that there are people in your broker team that understand what you do, and when you need help, it's there to be given. So they are there to arrange your insurance, identify potential liabilities, highlight things that you're not insured for, and give you guidance when you take on appointments. Tell you again things that are uninsurable and things that are onerous. Sometimes we have to take on onerous responsibilities, but it's best to know from the insurance company so that you can take a balanced view. So, PI, it covers us for financial consequences of professional negligence, legal liability, in partners, directors, members, and employees. And that last one's quite important because it's not unheard of for an employee to carry out some work, for the firm of consulting engineers to cease to trade, and people start to look at that employee as the person that gave the advice. And you're purchasing PI for your benefit, your company's benefit, not your clients. So beware the client that says, well, of course, you know, Nick, you've got all this PI. I'm sure we'll be okay, won't we? And just for context, in 2019, an 18-month policy for us was about 135k with, in fact, we had less than a 50k excess. It's now more than 200k, so it has gone up a lot. Do check it's worldwide or everywhere that you want to work, and make sure it's on a claims made cover, so each and every claim. There'll be an uninsured excess. It won't cover you for fines and penalties. It won't cover you for that wonderful phrase, fitness for purpose, because fitness for purpose implies a guarantee. If you're working for a contractor that's liable for liquidated damages, it won't cover you for that if they try to pass it on. And things like war, terrorism, nuclear risks, and supply of goods. So, things that we do here. We make sure we have a design brief. We make sure that we can validate the scheme, that it works. We get our staff and the different people working on it, if it's civils and structures, we get everyone to buy in on the fee so that they know how much they've got to spend. We check everything, or at the very least, we check the important bits. We validate our computer models by approximate hand calculations. And when things change, we have another look to make sure that we're not somehow invalidating the model that we have. And if it does change, I always say the stroke of an architect's pen can take, a week of a structural engineer's time. If it does change, then we must tell our client. And managing the risks. If we do find ourselves at the end of a claim, prompt notification to our brokers. Don't try and hide it. Don't try and work your way out of it. And really stay involved with the strategy. Make sure that you know what it is that your insurance company are doing to resolve it in terms of agreeing liability, the amount of the quantum, the amount that's being paid, and how it's being resolved. Although they're your insurance broker, it's your policy, and you just need to make sure that you know what's going on if the worst comes to the worst. Managing risk. So make sure we read our agreements. Make sure we remove onerous clauses, or at least mitigate them. Can we incorporate limitations on liability? Because if you end up in a dispute with your client, it will absorb far more time than the contract negotiations that you might do at the beginning of the job. So it's far better to do a little bit of hard work at the beginning, get the agreement that you want, or as close as you can, and you're the best one. You're the people doing the job, so you're the ones that are best to know the commercial relationship with your client. And remember that your client or your solicitor that gives you a formal appointment will have the client's best interests in mind, not yours. So, as I said before, look at limiting your liability. Pollution and contamination is often on an aggregate basis rather than a claims-made basis. Are you covered for asbestos? You might have a limit that you're covered for. Clients don't like this, but try to get a net contribution clause. So in other words, a clause that asks you to pay what is reasonable for your company to pay in the circumstances. Try and limit time. So in the UK, we have 6 years, which is a normal contract, and 12 years under seal. So clearly, the less time you're on the hook, the better. And try to get third-party rights excluded. This is something that came in the UK about third parties to a contract having the same rights as the people that had the contract in the first place. And just be aware of the wording. So using reasonable skill, care and diligence in performing its services is good. I've seen this one, the services will be supplied to the highest level. What does highest mean? Of skill and care in the industry by appropriate, experienced and qualified personnel. So that word highest is an absolute. What does it mean? The consultant will indemnify the client for all claims, penalties and costs. Well, that means that the client doesn't have to do anything but pass it on. So just putting the words in there, properly mitigated costs, makes the client or the contractor, if you're working for one, responsible for keeping those costs to a minimum. Beware of fitness for purpose, because it implies a guarantee and it's a strict liability. And the damages that are recoverable will be different from negligence. So just bear that in mind and try and avoid, or do avoid, fitness for purpose clauses unless your broker says that they're okay. Liquidated damages, these are things that contractors are normally liable for and quite often are excluded by professional indemnity policies. So again, make sure that when you agree working for a design and build contractor, for instance, that things like this are excluded. Asbestos and pollution and contamination, make sure that you know what you're covered for. And can you get a financial cap? Can you somehow agree with your client the maximum amount that you will be liable for? Clients don't particularly like it for obvious reasons, but it's worth having a go. And in the UK, we now have new forms of contract that require early warnings to clients and contractors. And of course, we're all nice consulting engineers. We all like to help out. But we are in a world now, in the same way as contractors have to give early warnings, we have to give early warnings under certain contract conditions. No bad thing, really. So finally, just make sure when you read your agreement, you read the words and place the literal interpretation on them. If the clause doesn't make sense, it's probably wrong. I've often been back to the drafters of these things asking what it means, and it often gets changed. What is it the client or the beneficiary is really trying to achieve? Try and use standard forms of contract. The ACE or the Construction Industry Council, you might have standard forms in the Republic. It's worth trying to get those. Every word and every clause will be there for a purpose. So make sure you understand what it is. And finally, I asked the client solicitor if they would sign the professional agreement that they're asking me to sign. And they can't say, yes, this is the brilliant thing, Nick, if actually they know it isn't. So ask the question, if you were advising me, would you advise me to sign it? And on that note, thank you very much.